So it is chemical cutting itself, but they are used wafering saw, which are making small wafers, thin slices you can call. If you remember the wafer biscuit, they are thin slices, and this wafer biscuit is very old. In the old days, when Pashtuns got guests, they used to make paratha for them with tea. But when education came, then the first biscuit I saw was wafer. And it was in 1970s and like that. And social people used to bring those biscuits. The farming and the other families used to use the old paratha or amrasa, those type of things with the tea. And even in some villages, even today, the engagements and other celebrations are done with amrasa type thing. They don't use the sweets which you use in the modern days, right? So that wafer biscuit and that crunchiness was because of those small, fine wafers. A string saw works by passing the string through an acid or solvent and then across the sample. Dilute acid to cut copper. And spark erosion is the electro discharge machining. I don't know much about this. And sometimes water is used. That the saw, if this is presume, let us that this is a saw and the sample is here, fixed here, and the saw is rotating. So here we use water as well. And that water just decreases or controls the mechanical damage to the sample. Because if the saw moves a little bit and powder gathers here, then the saw will get stopped. But when the water is passing on, it is keeping the mechanical blocking or damage to the minimum. So water is also used as a lubricant. It lubricates the functioning of the saw. In case of brittle samples such as ceramics, there are two cases. The one in which we do not want to introduce mechanical damage, and the second one we don't mind to introduce a mechanical damage or the material won't damage. Some materials, for example, silicon, sodium chloride, magnesium oxide, can be cleaved with a razor blade. So to remove this cleavage, we need to use a diamond wafering saw, right? There are, in the old days, people used to cut crystals along specific planes, and that planes can be, the crystal may be very hard. You can't cut it in the other way. But a specific plane, just like if you have experience of cutting or wafering in a way, the fine wood, when you start a crack, it goes up to the end, right? So you can easily do it, but in other words, you can't do that so easily. This crystallography is similar to that. At specific planes, the material is very weak and you can easily pick the various slices from it, and the proper crystal cutters are using those crystals as gems. When they are not damaged but properly cut through cleavages where it is easy to cut, then they are using those type of things. So water can also be used as a solvent on a spring saw to cut rock salt. Cutting the disc. In case of ductile materials, we can use ultrasonic drill in the case of brittle materials. But in the case of ductile materials, mechanical punch is used for cutting. A mechanical punch can cut discs with very small damage in the perimeter. Perimeter means along the edges. For brittle material, the three principal methods are spark erosion, ultrasonic drilling, or a grinding drill. In each case, the cutting tool is a hollow tube with an internal diameter 3 millimeter with sharp and thin walls. Right? The internal diameter here is 3 millimeter and the walls are very sharp and strong. Right? And they move with such a speed that it decreases the damage of the sample because of its sharpness and perfectness of the position. The position is not movable or like that. It is not loose. It is very solid at specific position. And when you are using the ordinary glass slide, it is not recommended for ultrasonic drilling. We used to find somewhere very hard glass so that it is very strong that the ultrasonic drill doesn't, the pressure couldn't break it, right? So we usually look for very strong glass. The spark erosion is used for conducting material. The ultrasonic drill vibrating in H2O and grinding drill remove material mechanically and are widely used for ceramic and steel conductors. If you are doing electron microscopy and you bought a machine for 100 million rupees, but you don't have silicon carbide powder, you can't use that machine. The silicon carbide powder may be a kilo for a few hundred or for a couple of thousand rupees. And where that silicon carbide powder is used, you put the sample here on a very hard glass like this, and ultrasonic drill is coming like this. It is like this hollow tube. And when you start it, you put silicon carbide powder here and a little bit water. So the pipe pressurizes those powder. The powders are very hard, just like diamond, right? And it is very fine. So when this ultrasonic drill moves, you will see sparks of light coming from there if you don't put water there. It will be so hot that that hardness will change the phase constitution, for example, of the material. And you put a little bit water as well here. So that silicon carbide powder in water makes the movement, the drilling, non-damaging, fine, soft. In a soft way, it drills the material. So if you have all the facilities but you don't have silicon carbide powder, then you cannot run an electron microscope laboratory. Right? It is very important that if you know something and something is not available in your country and you are asking for, I was fortunate, I started this laboratory with a horizontal ball mill. You see the two rods there on which cylinders are moved like this. So that was the first equipment I bought in Peshawar. And now when I look back 16 years, that I think I was a bit of mad that how can you make such a big laboratory from that small thing? But when you struggle continuously, and the times then helps you. Many people come and go and they help you, right? But if you are promising somebody that I am making an electron microscope lab, then you must be aware up to the silicon carbide powder. Otherwise, you will spend millions of rupees, but you will not be able to run machine. You will not be able to make a sample. So all these factors must be kept in mind that we need all these things for establishing a laboratory. The spark erosion is used for conducting an ultrasonic drill, vibrating tube, grinding drill, remove material mechanically, and are widely used for ceramics and semiconductors are also not totally metals, right? So the ductility is not usually there. That is why they are supposed to be treated like brittle material. Pre-thinning, the aim of this process is to thin the surface of the disc to a few micrometers, known as dimpling, as I explained it. Any damage at this stage can be removed during final thinning. Final thinning is that of argon ion thinning, right? Most mechanical dimplers use small radius steel tool. Tool is a small wheel. This is the wheel is fitted here. It has a screw and you fix it and the wheel is fitted here. And that wheel is called tool. Then you put the soft polyethylene type cloth, polyester type cloth there around it. And it's one side is sticky, the other is not. So you put the sticky part side onto the wheel. So it fits here, exactly fits here and is strong enough for dimpling the sound. Most mechanical dampeners are small radius tool to grind and polish the disc to a fixed radius of curvature at the center. As I told you, that it is like this. So this but this area remains almost the same. So it gives the strength to the sample after dimpling. One-sided dimpling is preferred to both side dimpling. Anderson made tripod polisher which can thin a specimen to less than 1 micron. There are many automatic machines nowadays available as well. But obviously, automatic machine means that you must be intelligent enough to use the parameters intelligently. Because if you are using 1 micron, there are 6 micron, 3 micron, 1 micron, a quarter micron, there may be half or different. So this quarter micron is only polishing the sample, but the other ones are grinding the sample. So when you, for example, if you use quarter micron, it only polishes the sample, shines it, but it doesn't grind the sample. So if you are using an automatic grinder, then you must be intelligent enough and smart enough to use the appropriate material so that your sample is not lost during that process, right? So it become things easier, make things easier, but again the human intervention and intelligence is important. Final thinning of the disc, electro polishing. This can only be used for electrically conducting samples such as metals and alloys. For this we use classical jet polish for one side polishing and a twin jet polish apparatus for two side, double side polishing. In both cases, laser beam or light sensor detects transparency and warning sound is given. So when it reaches a specific thickness, a beep or a warning sign appears and it tells you that don't go further in that area. Upon warning sound, the electrolyte flow is cut off to prevent loss of the thin area. Because once you get the thin area, then it is very, very risky. A little bit further thinning may get you rid of the thin area. Thick sample, you do many things, but when it reaches there, it is a very critical stage that you recognize that this is now the best sample. If you are pessimistic, that no, let me do it further, because an electron microscopist knows that if a little bit thick sample is put in the machine, it is usually useless. You can't do many things with that. But if you lost the thinness, that thin area, then again you can't do anything. So that is the critical stage, and your judgment that is the sample now best, or it can be made better, or it will worsen with time. These are the schematics of the jet, which array type thing emanates from that liquid, and it polishes the surface of the sample, and there it is double-sided. The sample is in the middle, the specimen you see, and it is the nozzles are on both sides, and they are chemically thinned down with the help of the specific chemicals. Ion milling, as I have explained to you several times, that bombarding a delicate sensitivity of 10 pm specimen with energetic or neutron atoms and sputtering materials from the film to make it thin enough. The ion beam penetrates the specimen to some extent, so we minimize this by the incident angle, right? So when the incident angle is higher, it will do deep grinding, and if the incident angle is shallow, yeah, when it's shallow, then it will just skip the surface and it will not go deep down, and you will have more thin area if the sample is near that critical state. A lower beam energy or a lower Z ion will do less damage. Z is atomic number, right? That if a low atomic number material is used, then the damage will be much less in comparison to the high Z well-used gases or materials which we use for ion thin. Sputter yield is equal to the number of atoms ejected per incident ions. Number of ion atoms ejected and incident ions, right? So from this you learn that how thinning occurs. You are ejecting individual atoms from the material at that stage, and that is why it's taking too long, and that is why it's a very critical step. What they have made here, that this is anode and this is the specimen disk, and vacuum. So the schematic diagram of ion beam thinning, it is just, you can say, the sample holder region, because whatever you do mechanically, it is a complete system, that how that sample holder is kept cold when the argon ions are hitting it. This is at a specific speed. So obviously the materials become hot, and you keep that cold through liquid nitrogen. You are keeping the system cool.